Bien, bueno, pues bienvenidos a todos. Entonces, el día de hoy tenemos el privilegio de tener como invitado a Justin McInroy de la Universidad de Bristol y nos va a hablar sobre la estructura de las álgebras axiales. So, today's talk is going to be Justin McInroy, and he's going to talk from the University of Bristol, and he's going to talk about the structure of axial algebras. So, welcome, Justin.
Thank you very much. Thank you very much, Alonso, for inviting me to give this talk. Yeah, I'm going to talk to you today about the structure of axial algebras. I'm going to begin with some motivation and a bit of history, where axial algebras came from and why we should be interested in them. I'll give you all the background you need, and then I will get on in the second half of the talk to give some details about the structure of axial algebras. So this is coming from a joint paper with Sanhan Khasraw and Sergey Shpectorov. Okay, so, oh, and if you don't understand anything at any point, feel free to ask questions. I'm more than happy to answer. Okay, there we go, great. So, by way of motivation, so axial algebras are a relatively new class of commutative non-associative algebra. So they were introduced maybe in the last 10 to 15 years. And they have a strong link to groups. And I'll elaborate on that a bit more in a minute. So one of the places they came from is from vertex operator algebras. So they axiomatize some important properties of vertex operator algebras. And for those who don't know about vertex operator algebras, they were introduced by physicists in connection with things like chiral algebras and 2D conformal field theory. But possibly more interesting for us is their link with, so one of the vertex operator algebras you might have heard of is the moonshine vertex operator algebra. And that's because it was used by Borcherds in his research on the monstrous moonshine conjecture. So in case you don't remember the monstrous moonshine conjecture, this links some dimensions of irreducible representations of the monster sporadic group. So I'll say a bit more about that in a minute, but it links some of these dimensions of irreducible representations with the coefficients in some number theoretic objects called the J function. So originally these were two totally separate areas of mathematics, and it was just noticed that you had this coincidence with different the same numbers coming up in both, and this is what led to the monstrous moonshine conjecture, and Borcherds and several others investigating this. Okay, so what else do axial algebras do? Well, they generalize some properties found in the Griess algebra. So the Griess algebra is the algebra which the monster was originally defined from. So the monster sporadic group was originally defined as the automorphism group of the Griess algebra back in the 70s, yeah, late 70s or maybe early 80s by Griess. Okay, other examples of axial algebras, well, if you've heard of Jordan algebras, very classical non-associative algebras, most Jordan algebras are examples, and also things called Matsuo algebras. And recently, some examples have been found in other areas of maths. So for instance, Tkachev looking at Hsiang algebras, I think that's how you pronounce it, in the theory of nonlinear PDEs, and also Fox looking at things like the algebra of Ricci flows. Okay, but so I'm a group theorist, so perhaps my motivation comes more from wanting to understand the monster itself, and also the classification of finite simple groups. So just as a reminder, what does the classification say? It says that if you are a finite simple group, then you are one of the following. You are either a cyclic group of prime order, so these are the abelian ones, or you are an alternating group, or I've bundled together quite a lot of things in this next category. You're a group of Lie type, so imagine things like PSL, NQ, or some orthogonal groups, symplectic groups, unitary groups, things like that. So in particular, all of these first three categories here, these are all infinite families. And then you get left with 26 exceptions, as it were. So 26 sporadic groups. These are groups which don't fit anywhere into those infinite families. And the monster is the largest of these sporadic groups. So, well, it looks like a very lovely theorem with 26 exceptions. So you might ask, well, why do the monster and these sporadics exist? Okay, so I want to tell you a bit about the Griess algebra and a bit about vertex operator algebras, just by way of motivation again. So, as I said before, the Griess algebra has the monster sporadic group as its automorphism group. And maybe 5 years after it was discovered, Conway was looking at it, and he showed that there was a bijection between some idempotents in the Griess algebra. So A is an idempotent if it squares to itself. So there's a bijection between some idempotents and some elements in the monster. And these elements happen to be of order 2 in this certain conjugacy class, 2A conjugacy class. And so because of this, he called these idempotents 2A axes. And a bit more than this, he showed that actually these idempotents, these 2A axes, they actually generate the whole Griess algebra. And a bit more than that, if you look at the multiplicative action of one of these 2A axes on the whole algebra, so it decomposes it as the direct sum of some eigenspaces. And these eigenspaces have eigenvalues 1, 0, a quarter, and 1 over 32. And also there is this restricted multiplication of eigenvectors. So I'll be a bit more explicit about what that is later. And okay, so he showed that there was this bijection, and I've just told you about what happens with the axes to start with. So the involution, which is associated to the axis, it preserves this decomposition. So it fixes all the elements which are in the sum of the 1, 0, and quarter eigenspaces, and it just inverts all the vectors which are in, or it multiplies them by -1, all the vectors which are in the 1 over 32 eigenspace. Okay, so there's this nice bijection between axes and automorphisms, and it preserves this decomposition. Okay, so what about in the vertex operator algebra world? So I don't want to go into what a vertex operator algebra is. It's rather complicated, but roughly speaking, the picture you should have in your head is it's an infinite vector space, but it's a graded vector space as well. So it has infinitely many finite pieces. These VIs here are finite dimensional, and it's the sum of infinitely many of these. And there are infinitely many different products on this vector space V, and they all preserve the grading in a certain way, and they're all sort of linked to one another in a rather intricate way. And there's a lot more detail as well, but that gives you a little bit of a picture anyway. So again, we talked before about this moonshine VOA, and it has the Griess algebra as its weight 2 part. So remember, the moonshine VOA was connected with the monster. Actually, its automorphism group is the monster, and the automorphism group of the Griess algebra is also the monster. And so maybe not surprisingly, it turns up as one of the graded pieces. Okay, and what did Miyamoto show? Well, he showed a similar type theorem. So he showed that there was a bijection between involutions in the automorphism group of the VOA, and this bijection is between these involutions and some conformal vectors, which he called Ising, or which are called Ising vectors. So this bijection, which we saw for the Griess algebra, it has a sort of analog here in the VOA world. And actually here it holds for a wider class of VOAs than just the moonshine VOA. So it holds for these OZ type VOAs, of which the moonshine VOA is one. Okay, so we've got this sort of nice property with this bijection, and can we make anything of this? So this is the idea for axial algebras. Essentially, this is the property that we want to capture. So just before giving you the definition, it might seem like a digression, but I need to make a small definition first. So I'm going to say a fusion law is a set F together with a symmetric map on F. And so it's going to take two elements of F, say A and B, and it's going to return you a subset of this set F. So this is my notation for the settable subsets. Okay, and so suppose I've got some algebra, capital A. I'm going to say that a small element A is an F-axis, or just an axis, if, well, I'm going to require that it's an idempotent. And I also want this decomposition property. So I'm going to say it's semi-simple. So again, this is just the adjoint action. So multiplication on the algebra. It's going to decompose the algebra as a direct sum of eigenspaces. And these eigenspaces are going to be indexed by this fusion law. And then finally, I'm going to require that the multiplication in our algebra satisfies the fusion law. So what I mean by that is that if you take a lambda eigenvector and a mu eigenvector and you multiply them, then their product should lie in the sum of all of the eigenspaces which are given by lambda star mu in the fusion law. So I'm going to be lazy and just write a lambda star mu for the direct sum of all of these. It's an easy notation. Okay, and I'm going to say that if an axis, or I'm going to say an axis is primitive if its one eigenspace is just spanned by the axis. So it's clear that because the axis is an idempotent, it's clear the axis lies in its one eigenspace. And to say it's primitive is just saying that's the only element in there up to scalars. Okay, well, let's see an example of the fusion law. So this is the monster type fusion law. This is the one which holds in the Griess algebra. So you remember from before that the eigenvalues I had for the Griess algebra were 1, 0, a quarter, and 1 over 32. And this is the multiplication table. And it's just telling you, for instance, that if you take a quarter eigenvector and a quarter eigenvector and you multiply them, then their product must lie in the sum of the 1 and the 0 eigenspace. So these should all really have set symbols around them, but it makes the table look a bit too messy, so I don't want to put those in. And also these two empty spaces here, these are the empty set, because if you have a 0 eigenvector, when you multiply that by your axis, you really get 0 in the algebra, not just a 0 eigenvector again. You get 0 in the algebra. Okay, so I've told you what axes are. So an axial algebra is a pair where you've got a commutative non-associative algebra, and you've also got a set X of axes. All these axes have to be for the same fusion law, and these axes, I'm going to require that they generate the algebra. So often I'm just going to talk about an axial algebra A without mentioning X, but always implicitly X is there. Okay, so at the beginning of the talk, I said that axial algebras have a strong link to groups, and I said that our motivation for defining them came from this bijection that we saw in both the Griess algebra and also in VOAs. So how do we get this bijection here? How do we get this nicely, naturally associated automorphisms? So suppose we've got an axis and suppose our fusion law is graded. Okay, so let's go back a minute and look at this fusion law. So we can see that this is graded. So if we just put the 1, the 0 and the quarter in the positive part and this 1/32 in the negative part, then you can see that if I do positive times positive, all these entries in here are in the positive part. And if I do positive times negative, I get negative. And if I do negative times negative, I get positive. So in that way, this table is Z2 graded. If you like, if I do that, I think I can even draw on it, yeah. So, so that gives you your grading. So suppose we've got one of these graded fusion laws. I'm going to define a map which just fixes everything in the positively graded part. So that's the sum of all of those eigenspaces which are in the positive part of the fusion law. And I'm going to send an element to minus itself if it's in one of the negatively graded eigenspaces. And it turns out that because my multiplication satisfies the fusion law, that was one of my axioms, my third axiom, this means that this map I've defined is an automorphism of the algebra. And this one here has order 2, so we're going to call it a Miyamoto involution. Okay, and now because we've got several different axes, each of these axes has a different decomposition of the algebra. And so we get several different automorphisms, several different Miyamoto involutions. So we can use these to generate a group. So I'm going to call the group generated by all these different Miyamoto involutions, I'm going to call this the Miyamoto group. And this is a subgroup of the automorphisms of the algebra. Okay, so have we defined anything interesting? So do we have any examples? Well, the Griess algebra is an example. So this is good because this was one of our motivations. As I said before, almost all Jordan algebras are examples. And these things called Matsuo algebras are examples. And what about the Miyamoto groups here? So for the Griess algebra, the Miyamoto group is really the monster. So we really have captured this bijection that we wanted to get, and this link between the Griess algebra and its automorphism group. For Jordan algebras, we get some classical groups and some groups of type F4 and G2. And for Matsuo algebras, we get so-called 3 transposition groups. So this is actually how they were defined. They're defined from 3 transposition groups, and you recover that 3 transposition group as the Miyamoto group. Okay, so I just want to look at these here and look at what groups we get. And I just observe that in this class of 3 transposition groups, we also have 3 sporadic groups hiding. So the 3 Fisher groups are hiding in here. And we also have the monster, so that's another sporadic group. And here, these give us some of the infinite families in the classification. So axial algebras are allowing us to view all of these groups in the same framework. So if you're really brave, or if you are ambitious, the great sort of hope in this area is do axial algebras offer a unified framework for finite simple groups? So that's clearly a very ambitious question. Perhaps a bit of a more concrete one is to ask, well, what groups can we get as the Miyamoto groups of axial algebras? So maybe to answer this first question, what we're really doing is we're changing the question, really. We're from classifying groups to classifying algebras. So how would you go about classifying algebras? I guess I just want to say something briefly about this for maybe 5 or so minutes before we get on to the structure part of the talk. So one thing you could do is you could fix a fusion law and try to classify the axial algebras with that fusion law. So what's the simplest fusion law you could think of? Well, let's take the fusion law, which just has a 1 and a 0 and looks like this. And it turns out that every associative axial algebra is precisely an axial algebra with this fusion law. So I said before that we were interested in non-associative axial algebras. What I really meant was, by non-associative, I meant not necessarily associative. So the associative ones are precisely these ones. Okay, so what's the next most complicated fusion law I could think of? I still want it to be graded, so it's going to look something like this. So I've got 1, 0, and an extra parameter here, eta. And this is called a Jordan type fusion law. And it turns out that when eta isn't a half, then these axial algebras with this fusion law are precisely Matsuo algebras. So these were these ones which are defined from 3 transposition groups. But what about for eta equals a half? So if any of you know anything about Jordan algebras, you'll realize that the idempotents in Jordan algebras, or some of the idempotents in Jordan algebras, have eigenvalues 1, 0, and a half, and they actually satisfy this fusion law. So Jordan algebras give examples of axial algebras where eta is a half as well. And the conjecture is that all of these are either Matsuo algebras or Jordan algebras. But currently this is open, so we don't know the answer to this. Okay, so before we had the monster fusion law, and if I were to skip back in my slides, you would see that it looked exactly like this, but just here was a quarter and here was 1/32. So this is a sort of generalized monster fusion law. And what about the algebras of this type? Well, this is currently wide open. So, I mean, we can't even classify all the ones for a quarter and 1/32. But we are making some progress. So the classification of two generated axial algebras of this type is within sight. So we know the two generated ones for a quarter and 1/32. We've known that for quite a while. But there are several groups who are, several people who are working on this classification. And in particular, Yabe recently, maybe in the last couple of months, he put a preprint on the archive which classifies all of these two generated ones under a symmetry condition, saying that the two generators here are, there's an automorphism in the algebra which switches the two generators. So this gives us a number of infinite families of these. So some of these don't depend on alpha and beta at all. Some of these depend on alpha and beta here, and some of them sort of only depend on one value, as it were. And these infinite families, so I've been told there are some algebraic geometers in the audience, so I thought I should mention some sort of algebraic geometry terms. So these infinite families, if you pick one of these infinite families, it doesn't necessarily exist for all values of alpha and beta. There's some variety which depends on alpha and beta, which is its existence variety. And what happens when you plot all of these varieties? Well, in particular, if you plot, say, the one-dimensional ones, there are only a very few points of intersection. And a quarter and 1/32 is one of these points of intersection. So somehow this is telling you that the monster is somehow unique, or well, it's distinguished among all of these groups which could come up as the Miyamoto groups in this case. You need all of these different algebras to exist, these two generated algebras to exist at this point to get the monster. Other groups might exist for several different values of alpha and beta. Okay, if I were talking to you before Yabe's paper, I would have said that we only knew a few infinite families and the only point of intersection was a quarter and 1/32. But now Yabe's paper shows a couple of other points of intersection, and I actually think it would be very interesting to look at those and try to figure out sort of what the unique groups come up which occur in these situations is. Okay, so there's actually a lot more I could say about on this topic here on sort of classification and what's happening in this classification of two generated algebras and so on, but I wanted to say today something about the structure of axial algebras. So it's clear that if we want to classify axial algebras and if we want to know more about them, we should be thinking more about their structure. So in this paper, Sanhan Khasraw, Sergey Shpectorov, and myself, we looked at a number of different parts of the structure of them. So two of the main ones are about ideals and about some decompositions, but I wanted to start with a topic which we call stability. So remember that I said that axial algebras have this generating set X, this set of axes. So if you think of some property of an axial algebra, does this property change if we change this generating set? So I'm going to say that a set of axes is closed if it's closed under the action of the Miyamoto group. So GX, the Miyamoto group here. And it turns out that there's a well-defined closure here. So I'm going to write X bar for the closure. And you can define an equivalence relation on sets of axes. So suppose I've got two sets of axes, X and Y. I'm going to say that they're equivalent if they have the same closure. And so now pick your favorite property, and I'm going to say that that property of the algebra is stable if it's invariant under equivalence of axes. So for example, what about generation? So suppose my algebra is generated by set X, and is also I've also got another set Y. And suppose that X and Y are equivalent. That means that they have the same closure. That means that this set Y will also generate my my algebra. So generation of my algebra is a stable property. So note, so also the Miyamoto group. So in particular, let's suppose you have a very small set X. So let's think about the Griess algebra for a minute. So it turns out the Griess algebra can be generated by just 3 axes. But the total number of 2A axes, this closure here, is hundreds of thousands. I think it may even be in the millions. But what this is saying is you can generate the whole algebra just using 3, or you can generate it using this much larger set. And in the same way, the Miyamoto group, so the monster group, can be generated by just 3 of these 2A involutions, or you can use all of the 2A involutions. So, so this is a useful concept, stability. So throughout the rest of the talk, I'm probably going to, I'm going to introduce some other definitions, and almost always with these definitions, they're stable. But I'm probably going to forget to say that. Okay, so I want to move on to my first topic, my first main topic, which is ideals. So in any algebra, we'd like to understand what ideals we get and how they interact. So let's begin with an observation. So suppose I've got an axis, and suppose I've got some subspace of my algebra, and this subspace is invariant under the adjoint action of this axis, so just under multiplication of this by this axis. Then it turns out that this actually decomposes my subspace into a direct sum of eigenspaces, where the eigenspaces are just the subspace intersected with the whole lambda eigenspace in the algebra. Okay, well, this already gives us a lemma, because if I have this decomposition, what does my associated tau involution do? It fixes all of these which are in the positive part, and it negates all of the vectors in the negative part. So it's just going to fix the subspace. So actually it fixes the whole of W. So if we've got one of these subspaces which is invariant under the adjoint action, then it's also invariant under the action of the associated tau involution. Okay, but I want to know about ideals. And what does this tell us about ideals? Well, ideals are obviously invariant under the adjoint action because they're ideals, and they're invariant under the adjoint action of every axis. So they're invariant under the action of every tau involution. but these tau involutions just generate the Miyamoto group. So that means that in an axial algebra, all of the ideals are fixed by the Miyamoto group. Okay. So what else can we say about ideals? Well, suppose we've got a primitive axial algebra. So remember, this is where the one eigenspace is just spanned by the axis. And suppose we've got an axis, and let's take some ideal. So as on the previous slide, this ideal can be written as the direct sum of these I lambda, eigenspaces in I. And what about the one eigenspace? So I've written brackets here to say that this is with respect to A. So this is the one eigenspace with respect to the axis A. So the one eigenspace, well, it can either be the whole of the one eigenspace, which is because it's one-dimensional, or it can be empty. So in particular, this is going to set up a dichotomy for us. So if we've got an ideal, it either contains some axis, A, or it contains no axes at all. So I want to split up my ideals and think about them separately. So suppose first that I think about the ideals which don't contain any axes. So we can prove a little lemma which says that, actually it's a bit more general. It says, suppose we've got a set of axes, some subset of primitive axes, then there's a unique largest ideal which contains no axes from this set Y. So in particular, if this set Y is the full set of axes in our axial algebra, so is X, then there's a unique largest ideal which contains no axes in my algebra. So this lemma is just telling me that this definition here of the radical of this unique largest ideal which contains no axes, it's just telling me that this definition is well defined. Okay, so I've defined this radical, and any other ideal which also contains no axes must be contained in this radical because it's the unique largest such ideal. Okay, but this may not be that easy to get your hands on what the radical is. So let's just have an aside a minute. So I'm going to define another thing which is called a Frobenius form. So a Frobenius form on an axial algebra is just a bilinear form on the algebra. I'm going to require it to be non-zero, and I want this bilinear form to associate with the algebra multiplication. So what do I mean? I just mean that if you have the value of the form on A and BC is the same as the value if you move this B across the comma. So it's the same as the value of the form on AB and C. Okay, so this is the definition of a Frobenius form. And it turns out that all the examples we know of axial algebras admit a Frobenius form. So in particular, the Griess algebra has a Frobenius form, and also vertex operator algebras, they have a similar type bilinear form, or an analogous one, as it were. And in another paper, Sergey Shpectorov and I conjecture that all axial algebras, at least a monster type anyway, admit a Frobenius form, and also that this Frobenius form is invariant under the action of the Miyamoto group. Okay, so why am I telling you about Frobenius forms? Well, they actually help us in calculating what the radical is. So suppose we have a primitive axial algebra which admits one of these Frobenius forms, then the radical of the form, or the perp of the form, is actually equal to the radical of the algebra if and only if the Frobenius form is non-zero on all the axes in my algebra. Okay, and just to note that all of the Frobenius forms that we know, these do have this property that they're non-zero on the axes. So why is this theorem important? Well, it might be a bit difficult to calculate what the radical of the algebra is. You know, think up an ideal which doesn't contain any axes and think of the largest one of those. But it's really straightforward if you know what the Frobenius form is to calculate the perp of or the radical of a bilinear form. So this gives us an easy way to calculate the radical of the algebra. Okay, so I should maybe go slightly quicker. So what about the ideals which do contain axes? Well, suppose I've got two axes and I can write my axis A, I can decompose it with respect to B. So I'm just going to write it as the sum of some A lambdas, where each of these A lambdas lie in the lambda eigenspace for B. And if A is primitive, then that must mean that the one eigenspace is spanned by just B. So that must mean that the A1 here is some scalar multiplied by B. And it turns out we call this scalar the projection of A onto B. And what I can do is I can define a graph. So I can define the projection graph to have vertex set given by the axes and a directed edge from A to B if the projection, so what we've just defined here, this projection of A onto B is non-zero. And what's the nice thing about this graph? Well, suppose I've got a primitive axial algebra and I've got an axis, an ideal which contains an axis A, then if there is a directed path in the projection graph which goes from A to B for another axis B, then B must also be in my ideal. So somehow the, if you like, directed connected components of this graph give you the ideals, or at least tell you which axes must be contained in ideals. But also remember that ideals are invariant under the action of the Miyamoto group. So what we can do is we can collapse this graph via the action of the Miyamoto group. So now instead of having vertices given by axes, I've got vertices given by orbits of axes and directed edges where I can find an axis in one orbit and an axis in another orbit with a directed edge between them. And so this proposition immediately gives us the version which just says I get an, so B is in my ideal if there is a directed path in the orbit projection graph from the orbit containing A to the orbit containing B. Okay, so this is giving us quite good control over what our ideals are and how they look. So I want to move on to the second of my main topics now, which is some decompositions. So suppose that we have an axial algebra A and it's generated by some pairwise annihilating subalgebras. So what this means is I've got this set of AIs, and AI times AJ is 0, but all these AIs generate my whole algebra. Well, if we have this set up, then it turns out that the algebra is actually the sum of the AIs as a vector space. So not only do these AIs generate my algebra, they actually span my algebra as a vector space. So I want to call this situation here in this lemma, if this happens, I'm going to call this a sum decomposition, and I'm going to write this box product here. Okay, so what about these sum decompositions? Well, these axial algebras have this nice axial structure, and in this lemma here, in this setup with my definition here, I haven't said anything about these AIs. These AIs are just some subalgebras. I haven't said anything about them being axial. So the question is, are they axial? So suppose I've got a primitive axial algebra which has one of these sum decompositions, and I'm going to let xi be the set of axes which are contained in AI, and I'm going to let bi be the axial subalgebra which is generated by this subset of axes AI. And it turns out that this set xi, this actually partitions x, so every axis is contained in a unique AI. And also, we have this sum decomposition in terms of axial subalgebras. So if your axial algebra has a sum decomposition, it has a sum decomposition in terms of axial subalgebras. So these sum decompositions do indeed respect the axial structure. So I'm not saying necessarily that these AIs are equal to these BIs, but there at least exists this sum decomposition like this. Okay, so I've told you a little bit about sum decompositions. So maybe you might ask, well, what's the best sum decomposition I can get? So what do I mean by best? Well, maybe a better way to phrase this is there a unique finest sum decomposition? So if I've got one of these sum decompositions, can I just keep on chopping it up into finer sum decompositions and then get the best one of these, the finest one? So suppose that I've got, let's think about this for a moment. So suppose I've got two of these subalgebras, AI and AJ. So they're pairwise annihilating, so that means that when I multiply them, I get 0. Well, obviously, if I multiply the axes in them, I also get 0 with these axes. So these axes are pairwise annihilating. So maybe this suggests another definition. So we can define the non-annihilating graph. So this just has vertex set given by the axes, and it has an edge between two of these axes if their product is non-zero, i.e. if they don't annihilate each other. Okay, and so why have I defined this? Well, it's clear that these xi's that I was talking about up here, so xi and xj, so xi must be a union of some connected components of delta. Because if not, if you're not a union of connected components, say you've got some other axis b, which is contained in one of these, but isn't it in your xi, then xi times b is going to be non-zero, but b must be contained in one of these xj's. So that's a contradiction. So we must have these being unions of connected components. So this suggests, well, what happens if I just take these to be the connected components? So the conjecture we make is that if you have a primitive axial algebra of monster type and you've got one of these sum decompositions, then in fact its finest sum decomposition is just given by the connected components. So i.e. the finest axial sum decomposition is given by a sum decomposition of BI, where the BI is just generated by this subset of axes given by the connected components in this graph. Okay, so that sounds like a good conjecture. So what progress can we make towards proving it? Well, why don't we think about the groups first? So it turns out that if you've got one of these sum decompositions, then the group, the Miyamoto group, is indeed the central product of the Miyamoto subgroups given by the connected components. So it turns out this is actually the best you could hope for here, this central product. So this is a nice, clean answer for the groups. It turns out that the algebras are rather more difficult to deal with. So we can get some partial results on the algebras here, but we need to impose some conditions. And again, the reason why it's more difficult is because, essentially because the algebras are non-associative. So I need a couple more definitions quickly. So I'm going to say that a subspace is a quasi-ideal if it's invariant under multiplication just by the axes. So an ideal, it would be an ideal if it's invariant under multiplication by all elements of my algebra, but I just want to require this just for the axes. And so, okay, so that's what a quasi-ideal is. And I'm going to say that the spine of the algebra is the quasi-ideal, which is generated by the set of axes x. So if I have my pen again, so actually things in my things in this spine will have the form A, B. So you'll have things which look like A. You'll have things which look like AB. You'll have things which look like A times things I've seen before. So A times B times C. You'll also then have A times things I've seen before. So A times B times C times D. Sorry, I'm writing with my mouse, so this is rather dodgy handwriting, and so on. But one thing you might not see in the spine is something which looks like AB times C times D. So it might be the case that this can be written in terms of things like this, but maybe not. But, oh, they've all disappeared. But if I'm going to say that my algebra is slender, if indeed all of those things that I wrote before, which is still there if I do that, so if my algebra is generated by things of this form, i.e. things which are in the spine, then I'm going to say that my algebra is slender. And by the way, it turns out that almost all the algebras I know are slender. I only know of a handful of examples which aren't. And I'm going to say that the fusion law is Suresh if 0 is in my fusion law, and also if 0 times any other eigenvector just gives me the set containing that eigenvector, or maybe the empty set. So all the fusion laws I've showed you today, they've all been Suresh. So what's the partial result? The partial result says, okay, suppose I've got an axial algebra which has one of these Suresh fusion laws, then the conjecture, which was on the previous slide, holds if at most one of the AIs is not slender. So I think this is a pretty reasonable theorem. I don't think Suresh is a terribly strong condition. And as I've said, almost all of the algebras I know are slender. So this conjecture actually holds for almost all of the algebras we could think of. Okay, so that is all I wanted to tell you. So thank you very much for listening. if you want to see any more details of this, it's contained in, this is the paper which has all the details of this. Thank you very much.
Okay, thank you very much, Justin. Great, thanks. Okay, so we have a time for a couple of questions. Is there any question? También pueden preguntar en español si quieren o en el chat. Okay, so in the meantime, yes, Sergey?
No. Yeah, I'm fine.
Okay. I wanted to ask something, Justin. Well, I have a couple of things. When you were talking about the section of the ideals that contain axes, so you made this graph with the projection. So I wanted to ask you that. Okay, probably this graph. You could do something equivalent in case the algebra has a Frobenius form, right? Maybe you can redefine this graph in terms using the Frobenius form as well. I don't know. I mean, because usually, probably. The first question is that if it's obvious that if this graph could be defined in terms of the Frobenius form, in case it accepts a Frobenius form, the algebra, and second, if you gain any extra information or anything extra, or it just gives you the same information.
So you're exactly right. It is linked to the Frobenius form. So if your algebra does have a Frobenius form, one thing I didn't tell you about Frobenius forms is that if you've got a Frobenius form, then I need to write quite carefully here. Different eigenspaces will be 0 in the form. So this is when lambda doesn't equal mu. So in particular, if we think about two axes here, and if I take the form on my evaluated on A and B, but I'm writing, okay, I actually decomposed A here, didn't I? So this is the sum of A lambda with B, but all of these A lambdas are just going to be 0 with B, apart from the very first one. So I'm just going to get that. So if this is non-zero, so A and B, the form on them is non-zero if and only if this A1 is non-zero, and that's if and only if this projection is non-zero. And so actually, if we've got an algebra with a Frobenius form, not only is this projection graph actually, it's actually undirected, i.e. if you've got an edge from A to B, you've also got an edge from B to A. And you can get the value, or you can tell when you've got an edge just by looking at the value in the Frobenius form.
I see, right. Yeah.
So in other words, if you've got a Frobenius form, you could write here the projection graph has an edge if and only if A, B is not 0.
Not 0. Yeah, sure. Yeah, this is okay. Great. Thanks. So here in the chat we have another question from Paz. So she asked about why in the fusion table, the first fusion table that you present, like how come you have these particular eigenvalues of 1/4, 1/32, or what would be? Yeah, I mean, why?
I mean, that's a good question. I'm struggling to find my fusion law at the moment, but yeah, it just happens that in the Griess algebra, these are the eigenvalues you get. The question why you get 1/4 and why you get 1/32 is sort of linked to what I was saying with when I was talking about the classification here. If you were look to classify algebras with this fusion law, if you had alpha is 1/4 and beta is 1/32, then that would be exactly this situation with this fusion law. And as I was sort of trying to say here, there are a number of infinite families of 2-generated algebras with this fusion law. And the monster happens only when you get the ones which are 2b, 3a, a quarter, 1 over 32, 3c, 1 over 32, 4a, and so on. So it needs every single one of these 2-generated algebras to form the monster. So that's a sort of answer as to why a quarter and 1 over 32 is needed, but it's just what happens. I think it's a really interesting question, why those values?
Yeah, it's still some of the mysteries of the monster still, right? So sorry, just what is this paper that you were making reference that you said that they find other intersection points?
It's a new paper by Yabe. It's on the archive maybe in April, something like that.
Okay.
It's called something like 2-generated algebras of Majorana, or 2-generated Majorana algebras.
Okay. No, actually, actually, it was in July.
Oh, July. Okay.
All right. Okay. Thanks. Yes, to check it as well. Thank you. Yeah. Okay, great. So if there are no more questions, we thank again very much Justin. Thanks for the talk, and yeah, I'll send you the link later of the talk. Okay.
Thanks very much.
Thank you.
Thank you. Bye-bye, everybody.
Bye. See you.